All right, so this is Isle La Motte, and we're looking at what I want to call the Chazy formation, Chazy. And as I just read on Wikipedia, it's a rock formation that extends from Quebec to Tennessee. So, fucking A. Here we are, and gonna look just close at some fossils. I don't know about this rock formation. I mean, it's a carbonate platform from what I think from a whole margin of Laurentia, right? The pre-Pangea North American craton out there in the I forget the name of the ocean. One of those big old oceans. Anyway, carbonate platform, shallow marine, tropical, very tropical waters, and I think they know that probably for a lot of reasons, but yeah, we have lime mud, which is precipitated in water at a certain tropical temperature, or it needs a certain warmth. But not only lime mud, we also have, holy shit, look at that. I haven't found anything like that yet. I've just been keeping my eye out. That looks to me, it's got to be some little fossil of some kind. I don't know. I don't see any other possibility there for that kind of regularity. Anyway, what I was about to say is it's not only lime mud, it's also fucking organisms, you know? So this is a reef, a tropical reef. And not only that, fucking world famous shit we're looking at right here. If you can trust what you read, which I generally do. And what they want to say about this is it's an Ordovician tropical reef. I forget. It's early, middle, late Ordovician. I forget now. But it's what they want to say is it's the oldest biodiverse reef. It's not exactly a coral reef, although there are corals in it, but it's a fairly stable, shallow marine ecosystem in which the substrate is the generously life-giving, lifeless bodies of shelly animals, filter feeding, and sessile animals, and it's not all sponges, as I was saying, but sponges are here. They used to say it was all spongy, but the interpretive signs are telling me actually the principal reef-forming organism is not a sponge, I think. Something else. So clearly a lot of people have been here. This is one of the more remote sites at the forget the name. It's the Good Cell Ridge or something like that. Okay, but I wanted to just, all this shit is new to me. It's really wonderful, and you can kind of see with the mottled surface. These, I wanted to focus in here. I found this little chunk. Let's see if this works. Ooh, you like that? You like that? I could get, oh yeah, beautiful. See that little star? So that's a echinoderm, And that's a little segment of a stalk of a sessile animal, common name sea lily, filter feeding, and they're 5-parted little plantoid animals, although they're not plants at all, but they're there's another one that's been sort of smooshed. These are these fun little segments of the stalk, and the stalk comes in these little jointed, stacked, these little cylinders or these little discs stacked on each other. And I think what we're seeing there is this sort of the calcareous, backbone, so to speak, the xylem, and within that 5-pointed area would be various. I just don't know, not the phloem, but I'm just riffing here. But anyway, echinoderms in the wild on the Chazy Reef, and I think what I'm just gonna do is look at fossils as they come up and learn about them and caption them, because if I start theorizing in the field, it's a slippery slope on this extremely non-slippery limestone. Crown point, extremely non-slippery crown point limestone. Okay, so yeah, sound change here because I'm doing this recording in the studio, and we will be looking at fossils, but I think first we'll zoom out and just discuss broad sort of global geological questions about carbonate platforms and shallow marine continental margins, and we'll look at some maps. All right, well, I get this is pretty weird, pretty funny, pretty weird. So yeah, the first step we're going to take here in pulling the camera back is just looking at the entirety of the continental margin of, roughly where we are. So, I mean, this is Cape Cod and Nova Scotia and the Gulf of Maine and Georges Bank, and I guess where we are with the Crown Point limestone is up there in the upper left, and we see that the continent by no means ends at the frickin' seashore. In short, no sir. It ends at the frickin' transition between the continental crust and the oceanic crust. And between the land and that point, we get the shelf. And this is a kind of geologic setting created through erosion and deposition of continental margins of all kinds, in which we can find carbonate platforms, which are these environments in which we get limestone deposition. Yeah, so check that out. That's the freaking, that's our continent, that's the edge of our continent there. And, where we last were was in the upper left, but yeah, the carbonate platform, and, a lot of times, and this is the kind of world in which limestones are created, basically. It's a very, and you can see this. You can see this in action. You go down to the Bahamas, and you go to the Yucatan. You see these sort of much more recent limestones, that have been, I guess, pushed up somehow, because they're eroding above sea level now. But yeah, those are recent, and but the Crown Point limestone, that's ancient, right? That's almost 500 million years old, 460 million years old. The Earth itself would be, I think, about 4.5 billion years old, so 4,500 million years. So 500 million is like less than 20%. I'm terrible with math. I'll do that later. Anyway, 500 million years is a long time. What I'm trying to say is a long time, but it's not like the longest time you ever heard of. You know? In geology, that is. How did we get on this? Okay, anyway, yeah, there's our beautiful shelf. And yeah, so check this shit out. You got slide 2, world continental shelves and mid-ocean ridges. So this is a fucking gorgeous map. I don't know about you, but this is the kind of shit I lose my breath. Yeah, so this is an amazing, this is the kind of map that you could look at this for a long time, see some cool shit, man. Never stop seeing some cool shit. So yeah, the land, everything above water is just black, which is nice for a change. And then we're just looking at the depth of the ocean. Basically, I think it's bathymetric. I'm pretty sure, bathymetric. So what that means is the purple or the blue is the purplish is the deep, the real deep, then blue, then light blue, then green is shallower, yellow is shallow, and then orange is the shallowest. And that's just the depth of the ocean. But what stands out when you do that is this amazing highlighting of the world continental shelves and also the mid-ocean ridges, the places where curling down there from Madagascar between Australia and Antarctica, and then up through the Pacific, and then kissing onto the North American continent there around the northern bit of Mexico and so forth. That's this great mid-ocean ridge system. I don't know, maybe I don't know if that's a whole thing. Maybe that's many mid-ocean ridges. And then we got another nice one running down through the Atlantic that's kind of tucked off to the side with this view. And those are areas of the world where we're getting a phenomenon called ridge push. And that's there's an upwelling of the mantle underneath that, and the fluid mantle underneath the earth and underneath the crust, underneath the lithosphere, and it's pushing up. There's these flood basalts bubbling up, but it's also pushing up and then pushing out from there. But then at the same time, we get a phenomenon called slab pull, and ridge push, slab pull. And slab pull happens at subduction zones. Ridge push happens at mid-ocean ridges. And a subduction zone is, a place where the crust got heavy and thick, maybe, cold. It cooled off. It got heavy, thick, cold, and dense. And I don't know about thick, but just definitely heavy and dense. Heavy in relation to the surrounding and to the underlying mantle material, you see what I mean? Underneath that crust. And as soon as it sort of detaches from the continent, it starts sliding down under the continental crust at a subduction zone. And the fucked up thing is that this is a fairly quote-unquote fast process in sort of world geologic time, considered in world geologic time. The ocean, there's no oceanic crust anywhere in the world older than 200 million years, which is an astounding fact. I mean, when people figured that out, it fucking blew their minds. They're like, what? Why? In the 60s, they're like sitting there scratching their heads. These fucking World War II sort of geophysicist dudes, and they went around in submarines and measuring shit, and it's an awesome story, actually. It's really, awesome in the sense of a good story. It's instructive because geology is intertwined with capitalism. Capitalism is intertwined with war. And yeah, World War basically was required for world geology to become accessible to the human brain, the human mind, and to scientific inquiry. So that's just a fucking fact, and we're just gonna mention that. But look at these shelves, baby, and in the Bahamas, down there around Florida, we have the continuation of the eastern North Atlantic margin, the continental margin there, and the shallow marine. Down in the Bahamas, we got that limestone, and it's marines, microscopic marine animals with little, calcareous skeletons and getting ground up and shelly stuff, and it just becomes lime mud, but all these fossils can be mixed into it. And that's what we're thinking about. And so slide 3 is like this reminder of the beautiful complexity of these geologic processes. I'm talking about slab pull and ridge push. To go back for a second, actually, like ultimately, what are we talking about? We're talking about the enormous titanic energies rolled up into a beautiful ball 4.5 billion years ago, and actually through in a multi-layered process of various events, including a Mars-sized planet slamming into the Earth. I think back around 4 billion years ago or something, and all these energies are added into the Earth, and then it's orbiting and cooling, right? Cooling and orbiting and cooling. And the continents move around, and that's just a reflection of the cooling of the Earth. But they behave in this amazing way. They accrete, they fault, there's continents, there's continental crust, there's oceanic crust. They're radically different beings, basically. The poetry mounts, the poetry accretes. There's no denying it, and it's just a remarkable thing. So when we talk about slab pull and ridge push, we're just talking about the process of the Earth, or the orbiting Earth, cooling off, but it's mixed up with all sorts of things, and it generates, and ultimately it generates this mosaic of settings, mosaic of habitats and ecosystems and continental shelf that we're focusing on. So if we focus in on this and we look at it in this sort of total geologic picture, we're looking here at the beautiful geologic complexity of the zone where the oceanic crust meets the continental crust, right? And there's many different ways it can be underneath the overlying sediments, but here on the right-hand side of these 3 images we're talking about the shelf. That's the shelf, the beginning of the shelf. So we're looking here at the zone right between the orange and the blue, right there. This sort of, that canyon carved ridge, canyon systems, on George's Bank there on slide 1. And but here we see cross sections of this. COT is the continent oceanic crust transition, the continent ocean transition, and then the moho is this word that geologists use in honor of the first hero of thought. Some dude, his name I think was Moho or so, and that was the first part of his name. Maybe that was his nickname. I don't know. Anyway, it's just some dude's name, but that's what they call the boundary between the lithosphere and the mantle, I guess. The between the crust, the relatively rigid crust, and the significantly non-rigid, underlying areas. And the crust slides on the non-rigid areas. It slides remarkably. And, we're just looking at the various processes. It broadens. The questions broaden. But yeah, we're keeping in mind that shallow marine environment up there, and as we even zoom even further out to, this whole beautiful aspect of the aliveness of the Earth, which is what they call the Wilson cycle. Again, just some dude named Wilson, but it's not a hard and fast rule that's rigidly observed. There's all sorts of variations and contingencies that sort of disrupt the pattern, or can disrupt the pattern. Different smaller supercontinents can form. There's all sorts of variations, but in general, you get about every 500 million years, every half a billion years. So, twice every billion years, or 4 times every 2 billion, 6 times every 3 billion, 8 times every but maybe it wasn't going back that far. Maybe there was a different way that the continents had of being back then. Research continues. Anyway, in the present configuration, every 500 million years, on the general average, the continents form a supercontinent, and then in the next 500 million years, they break up and form a different supercontinent. So my point is, you have to start thinking of the movement of continents, which is only about as fast as your fingernail grows, as a very fast movement in geologic terms, which is to be, it's not to be sneezed at. In a person's lifetime, a whole continent will move, I don't know, what, like 5-10 feet, something like that. It's pretty far, in just a person's lifetime, a little person, and the Earth is really old. So 5-10 feet, and that is going pretty fast. And, another way to, if we go back, if we go back for a second to slide 2, you see there that all that oceanic crust that we're looking at is very young, very recent. And so another way, like these continents are moving fast, another way to put that is no oceanic crust is... Oh, did I talk about that already? I think I talked about it already. Oh, good for me, good for me. Yeah, and so it might be related to these different patterns of convection current in the fluid mantle that we see schematically laid out here, but maybe not, in slide 4, maybe not. It's just a hypothesis, but they do come together and then break up, and it makes sense that they break up because heat is going to get trapped under that thick blanket of fluffier rock, which is what the continent is. You can see them, they're buoyant, right? They're buoyant there in the fluid mantle, and you see the oceanic plates subducting down. They go pretty far before they get melted, because they're cold and dense, and they go down, I think, hundreds of kilometers into the mantle, I read somewhere. But it's a schematic drawing still. But yeah, you see that supercontinent, the little arrows underneath have nowhere to go. And so eventually it breaks open, it rifts in the zones where it's weakest. And that has to do with how it came together in the first place. And then it rifts and then accretes in a different way, right? Because the rifting sets it off on a different path, and then it all comes around again. So there's this wonderful circularity. And as that happens, this is a fucking bonkers, beautiful, beautiful geologic wisdom embedded in this image. Because, the continents have just been moved around so much. It's just staggering, right? And this image really unlocks that reality, because The dark gray bits that's the ancient of ancients. That's the crust, the Archean crust, the Archean rocks, which are rocks older than 2,500 million years, right? 2.5 billion years old. Older than that, 3 billion years, 3.5 billion years, 3.8 billion years, very old rocks in these places. And I have to go check them out. Look at that, right up there around Hudson Bay, right out there in Michigan. I think it crops out these amazing rocks, 3.8 billion year old rocks. They're full of iron. They're full of iron from a totally different world. But there they are. And they form the stable core of these continents that are accreting and breaking up. And this is a beautiful image because, so the dark is this really ancient Archean crust that those cores have been in that. We have the slave craton, the Hearn craton, the superior craton there. In Wyoming, that's a different story. But the Trans-Hudson, I don't know. But those bits have cohered for as old as they are, But the lighter gray areas, that's Proterozoic continents. So that's before the Mesozoic, before Pangea times. You had the Proterozoic, and there's life, begins with the Cambrian, and that's the beginning, of really serious evolution. Evolutions really takes off in the Cambrian. It's fucking bonkers fast in geologic terms. I mean, again, talk about things that are fast. 20 million years it took or 50 million years, something like that, it took for the basic body plans of all life to develop and form completely. And now there's just variations on those themes, right? But that only took 50 million years. I mean, that's so quick. A species, I think, mammals, like for the last while, a mammal species tends to last for maybe around 2 million years. I personally think the human species is in its own category, and it will probably last for much longer, I think, even in millions of years, but that's a whole nother question. Anyway, but these Proterozoic continents are laid out there, and you get a feeling for the crazy way the Earth was, okay, in the present day. But now, finally, we jump to slide 6 and to Gondwana, and to 480 million years ago, so 20 million years before the Crown Point limestone and those fossils and everything we were looking at was formed. We had a world like this, and this is an amazing map. I've never seen this until just when I looked it up to make this part of the video, and it's incredible. I mean, so we're looking at the South Pole there, right in the center, and that's the whole world flattened into a circle, right? Flattened into a circle, and you can see the equator there is a ways out from the center, and then the distortion radically accelerates until that outer circle is in fact the North Pole spread to this crazy distortion, right? But there's nothing out there. All the continents are clustered around the South Pole, so this is a wonderful way to and all that's out there is the Panthalassic Ocean, fucking huge ass ocean, man, just crazy big ocean. And so we have Gondwana here in the South Pole. So, and Laurentia, there's Laurentia over there on the left, and you can see they've put in the present day outline of the continent just to place it, just for reference. and they've even put in some extent. Yeah, they've. Are there any political boundaries in this map? I don't quite think so, which is kind of nice. You know, they oftentimes use political boundaries as references, but I think it's just actual boundary. Maybe some of the Africa lines. I don't know. Northeast Africa, Northwest. Oh no, those are starting to rift. Those are. I don't know. All these interesting questions. Anyway, this is an amazing map. You could look at this for a long time. It's zeroing in again on those shelves, right? That blue is the shelf. And we see just an incredible amount of shelf. The shelf to dry land ratio is very high, you know. Unlike, if we go back to this slide 2, you know, it's pretty low. There's much more dry land than shelf here. But we're going 480 million years ago, and things are quite different. And things are laid out here in a beautiful way. You have subduction zones in blue lines with the arrow points in the direction of subduction. So basically, the oceanic plates out in the Panthalassic Ocean are subducting under Gondwana, for example. They're subducting under most of Gondwana. They're also subducting under Laurentia, which is going to push Laurentia, right? It's going to push it. Or I think, you know, the continents are being massed together here at 480 million years. We see there's already a pretty big supercontinent, Gondwana, with present day South America and Africa totally sandwiched together, along with East Antarctica, and West Australia for good measure. And yeah, they're coming together. We see all this shelf, and it's zeroing in on brachiopod provinces. So they're looking for brachiopod fossils and representative sites of various brachiopod, you know, in these little green boxes and so forth. All these little things, these different assemblages of brachiopods. So what is a brachiopod? It's an animal. It's something. I gotta look it up. It's a little shell, I think. But it's an index fossil. You know, it's the kind of fossil that tells them, oh, we got a shallow marine environment. You know, it can really pinpoint time because they've identified the species, and you know, they know that species went extinct at a certain time. It's not found in any older rocks, so they can pinpoint time. Anyway. Yeah, so we've made it back to 480, but now here's 450, you know, so slide 7, and we can sort of toggle between them. It's kind of interesting, you know, at 480, focus on Laurentia, it stays kind of in place, but you can see it's sort of twisting. It's sort of twisting a little bit, right? It's rotating, and Gondwana, too, is rotating. They're kind of turning toward each other in this interesting way. But Siberia and Baltica is kind of, and whoops, I jumped to the wrong. Siberia and Baltica and Avalonia is where the action is. You can see Avalonia is pretty close in 480. It's pretty close to Gondwana. It's just split off, and then in 450, it's all the way out there on the other side of the Rheic Ocean, and there's a mid-ocean ridge between there. These are just reconstructions. These are just hypotheses. I mean, these are theories, but they're refined, you know, they're refined. And this is a very recent one, 2020. So they're researching paleogeography using brachiopods, and they're looking at climate change, and that's reflected in the way rocks are formed and species are co-extinct and so forth. So yeah, 450, this is 10 million years after the Crown Point limestone was deposited. And yeah, we see some activity there on the Laurentian margin. We see that subduction zone. So actually, you know, I think in the late Ordovician, you know, the tectonic orogeny is really getting going, and that's that subduction zone. Laurentia is bumping up. Laurentia is not Laurentia's got some oceanic crust subducting under it, and I think there's volcanoes coming up on that margin now. But if we go back to 480, we see it's a wider margin, so as those volcanoes continue to subduct, mountains are getting built along that margin and basins are forming. The crust is doing wild and wonderful things. And here's yet another image of 450 and 480 from the same paper. These different brachiopod provinces in different colors there, but they're associated with different continents. So you have the Laurentian brachiopod benthic faunal province, and you also have the Baltic one and the Siberian one there, S, and and others. And Gondwana in this view is kind of shoved out of sight. So now we're going to take a kind of journey through time back to the present, and do a pretty quick, in five slides here, a quick kind of review of or maybe an introduction, depending what you are, on this area, just zeroing in on the kind of overall picture and just how the kind of story that geology allows us and invites us to carry around in our heads as we look at this limestone and look at its fossils and think about the reefs and sort of picture it. We have to picture it on that Laurentian margin out there, getting subducted under, maybe with some volcanoes on this oceanward side, because there is some sandstone underneath our limestones, and that sandstone had to come from a mountain. Sandstone doesn't just pop up out of nowhere. It has to come down off a mountain, baby, and it has to mass there on the beach. And what mountain was that underneath our limestones? We're thinking the Tectonic mountains, and that's that subduction zone I was pointing to there in slide 7 along the Laurentian margin. Avalonia coming in, about to collide, but before that happens, and Avalonia collides, that's the so-called tectonic Acadian orogeny. That's a Acadian mountain building event. All the different mountain building events on the Laurentian margin, up to and including the Alleghenian when Gondwana hits, are part of a single super process. They're not discrete beginnings and endings, little neat things. They sort of fold into each other. There's a lot of tectonic activity as Pangea is formed in various places, where if it's not in one place, it's in another place. Anyway, another thing to point out here is just how you can see the seas are fluctuating. So in 450, almost all of Laurentia is covered there. It's incredible. It's been floating by itself in the Panthalassic. You have to give it some credit. For about 500 million years, it's been floating there by itself. Not floating, but, skittering. I don't know. You're getting pushed around by the place, but there hasn't undergone a mountain building event. It's a long time of just peaceful evolution in those warm tropical seas. Nothing much happening on land. Maybe lichens. Lichens? I don't know. Don't quote me on that, but not too much, in the late Ordovician. You got to be more in the Devonian for life to really get going on land. But it's okay, because you have the equator running through all those shelf habitats, and that's just unlocking. Life is just, those body plans, like I talked about during the so-called Cambrian explosion. That's already happened, Cambrian, Ordovician, and so forth and so on. But yeah, there it is, and the sea is coming up, and it's just so much to love, so much to appreciate, and it all connects back to the Chazy Reef and the Isle La Motte And, the fucking French conquistadors that gave these parts of the land their names. Oh, killers, killers like many. So here jumping forward, trying to bring it back to our coming forward. It's a big jump here between 450 there on the bottom with the different continental sort of masses, set out like that. But you can kind of see Gondwana is going to come up, kind of squeeze up the left side. Laurentia is going to rotate in, and they're going to but before Gondwana and Laurentia meet, Baltica and Siberia are coming into play. So this BAW here on slide 8 with the 450 million years on the bottom, that's Baltica, that area. You can see the coastline of Norway as a reference there, what land that is. And at 340 in Mississippian times, Baltica is totally sutured on to Laurentia, and actually they call this now La Russa. I think that's La Russa, and it's got its own name to designate after that suturing. But that's the Caledonian orogeny up there, and that's like Greenland and stuff as that's exposed now. Siberia is kind of off by itself, but it's participating. It's up top there in this view. So that's just to say you can see it's a big jump, but to 340, but you can see things are coming together. And now here's some quicker jumps. Boom, Pennsylvania, and that's 440 million. Look at all that shelf habitat, just creatures love that. And then here's 280, and here is the early Permian. So here is like you can see that huge mountain belt right on the equator. That's the Appalachian Mountains, and the Appalachian origin, they call it. And now it's, spread out between Africa and the U.S. and or North America. But yeah, so this is fun to look. So 340, 300, 280, you can see that what's happening. It's just a fun flip book thing. And this, I gotta stop. This is too late. We'll pick this up, or this is like halfway. So this is a lot. This is good. Am I really going to do this? Am I really going to talk about, am I really going to talk coherently and yet poetically about the lithotectonic map of the Appalachian orogeny that Hibbard et al. Completed in 2006? I guess probably a monumental undertaking. I still see it reproduced, cited, so I'm doing the same. I have it on my wall. I spent a long time looking at it. It's an amazing way to connect with the Appalachians. And just to make sure we're all on the same page there, that the equator is now Appalachians are almost tracking the equator, and it's a massive mountain belt. It's much higher and bigger than the present day Himalayas at its height, and it's interesting if you watch a animation of the sort of route traveled by the continents that they've sort of reconstructed. They're readily available on YouTube. Steve Scotese, I want to say, is one of the authors of that kind of work. and this is his work that we're looking at now. In fact, he has these animations, and when Pangea comes together, and the suturing of Gondwana and La Russa, it just grinds against the pressures that brought it together. In fact, remain in operation for millions of years, and things kind of come a bit to a stop tectonically because everything is a little bit stable there. I mean, until that heat I was talking about before builds up underneath that big blanket of continental thick but less dense continental crust, and the continents part ways for a time. The cratons say, well, that was a fun party, and now it's just getting time to move on again, back into, because there's that massive ocean out there. It needs companionship too. Island arcs, we want more island arcs. We want more microcontinents, and we just need some space. We need some space, and it's a beautiful thing when the cratons decide to do that, even though it often unleashes mass death. In fact, the geology of the Earth is not only a kind of rhythm and engine of life in normal times, but in specific times, like when there's the breakup of a supercontinent, you have lavas coming up, and all hell breaks loose, and many things die. This happened at the end of the Permian. And the most cataclysmic of all mass extinctions was the end Permian, and truly mind-bending disaster in which really life itself came close to reverting back to single cellular, but it didn't, but it kind of came close. Anyway, a different kind of mass extinction than the one currently underway, because the one currently underway is it's not controlled and constrained by geology. It's controlled and constrained by, I hate to say it, but human politics and war, basically, and capitalism. So it's a qualitatively different kind of mass extinction, and thank God, the one we're doing is not going to be as bad as the one at the end of the Permian, but it's still going to be bad. It's still a mass extinction. We live in a the air we breathe is just suffused with death, because there's just so much death and disruption all around us of the whole biosphere, and we're doing it. We, quote unquote, except that's a political we, and that's, but we'll set that aside. In any case, the breakup of Pangea, went forward, and you can kind of get from this 280 map, if we jump back to world map, you can kind of see what's happened, right? Africa and South America have parted, obviously. North America has, if we're looking here at 280 million years ago, North America has rotated, and now it's sort of dancing with South America, and the whole Atlantic Ocean is opened, and the southern part of Gondwana, that's very low down, has rotated up and become or it's actually split apart and become Antarctica, Australia, and so forth, but also all of Asia has been assembled, with significant participation from India, which has a mind of its own. That it's not a huge continent, but it's really, it's building the the Himalayas. Okay. Yeah, so here we come into the present then, and we're still looking at, we've actually rotated the present world back, in this view. It's a little bit akin to that view in the early Permian, with the Appalachians horizontal, and we're looking at this middle section of the Appalachians here. If you take a moment to get oriented, you see the Gulf of Maine off to the lower right, the hook of Cape Cod, Massachusetts, what they call here the New York Promontory, except it's where Long Island and the Atlantic coastal plain meet there, and so forth and so on. You can see Lake Ontario up there at the top. And Isle La Motte is in that little red box that I've drawn in. It's in fact a small place within that box. And what this map does is it takes that very complex, if we think back to 450, 480 million years, and especially with Avalonia here coming in between the Rheic and the Iapetus Ocean, that docks onto Laurentia and in the so-called Acadian orogeny, and forms big mountains, so multiple waves and multiple accreted terrains. That's what this map really highlights. Multiple, waves of different things arriving, different kinds of things arriving, and I like to start, and this is fitting because it's kind of what we're doing in going to look at these carbonates in Lake Champlain. Is we're going away from the continental margin enough, away from the present day continental margin enough, away from George's Bank until we meet the pre-Pangea continental margin of Laurentia, right? And it's deformed and it's lithified, but there it is, and it's in that, especially in this view, it's in that light blue color labeled as number 4. The darker blue color, number 5, is also from the passive margin, from the continental margin that's just out there in the ocean, not undergoing, it's tectonically inactive. That's what they mean by passive. It's not an active margin. It's not being... there's no subduction going on under it, and it's not crunching into another continent. That blue color is also from the passive margin. So the light blue and the dark blue are parts, are those rocks. Some of them are blocks that have been uplifted and they interfinger those they mixed in with those rocks. That brown color is what we're looking at. The Isle La Motte is brown color, and it's labeled as 6B. It's a little hard to see, but yeah, they call that 6B. And here we are zooming in, 6B, and Isle La Motte is... Isle La Motte, I think they would say, is the upper left of this this red rectangle. It's the It's the small island with the little black line right at the end. What that line denotes a normal fault, a place where extension took place in the crust, and there was displacement along a fault. Just a fault in the rock. And anyway, so that's where we are, 6B. And yeah, you can see if we go back here, what this map shows us is that this is the so-called Great Valley of the Appalachians. The Great Valley of the Appalachians is where exotic terrains of various and island arcs. The island arcs here are green. You see those green colors, both light green and bluer green. Those are these. Those are the squeezed. The squeezed material accreted from island arcs, and but the Great Valley of the Appalachians is the pre-orogenic passive continental margin, that peaceful continental shelf, turned into limestone or marble. If it's more in the thick of the origin, it's likely to be marble. But limestone and marble dissolve in rainwater slowly but steadily. They dissolve in rainwater because rainwater has a certain amount of CO2, which is makes it an acid, a mild acid, that's the Great Valley of the Appalachians, a strip of weak rock, as John McPhee quotes a geologist saying, and it runs throughout. There's a geologic signature kind of contained in those carbonates. So, and those limestones and those marbles and so forth, and dolostones. And it's a beautiful thing. The mystery of the reality in which, you drive into the interior of the continent, and what do you find as you come down out of the mountains, in North Adams, for example, or Burlington, or these various places. What do you find? You find this long, beautiful valley with underlain by limestones and marbles and carbonates, and it goes forever. It goes forever. It goes down through the whole Appalachians. It's part of that whole structure, and it's. It also has sedimentary rocks in it. Like I was saying, the bits and pieces of the Tectonic and the Acadian orogenies are in it, and it's been thrusted and faulted by the pressure of Gondwana during the Alleghenian orogeny, that big mountain belt of the assembly of the really huge Appalachians. But in 6B here, what we have is some of the early sedimentary rocks, the sandstones, that came down off the Tectonic mountains. So these subduction zone. I guess they call that a magmatic arc, maybe, mountains, and into the foreland basin of the continent, onto the foreland basin. So the 6B, those sediments, that's the Hibbard calls that the tectonic foreland basin units of rock, and it has some sandstones lower down, and then carbonates, and that's just a part of the crust behind that. So if we go all the way back here to 450, that's in the middle of the tectonic orogeny. And if we see there just to the right of Laurentia, there's that little diamond, but then there's that little reddish star, and that little reddish star denotes volcanics, right? So this is after our rocks have been deposited, but if we go back here to 480, we see there's a whole line of volcanics further out along Laurentia, right? So those are coming up, but to the to the cratonward side of those volcanics, there's still a shelf, right? So the mountains are just beginning to come up, and those are the rocks we're looking at there in Isle La Motte. We have some of the sediments of those mountains that are just beginning to come up, but mostly we have carbonates from that beautiful inland shallow marine. I mean, it's just a little bit inland, but it's still it's what they call the foreland basin of the continent. It's just a sort of the foreland is the front land, as opposed to the hinterland, as opposed to the core. Okay, and now we get really detailed. Boom. We have Isle La Motte here over on the left. Now we're inside that red rectangle. That's basically what we're looking at here. And this is the really detailed state map. And there it is, Isle La Motte. And you can see how special it is, partly because the beds of carbonates there, ODP, OCP, OV, OGF, OCHD, OSP, going up there, going north in Isle La Motte, over on the left with that stack of darker colors. Those beds of carbonates are dipping gently to the north, in fact. And so what that means is, since they've been planed off horizontal by the glacier, we see the whole stratigraphy. We see the whole sequence of time embodied in those carbonates, in the different carbonates. So I have here the Chazy group is OV, OCP, and ODP, right? So you see it's below that little tiny band of OBR. And that's what we're looking at. That's the Chazy group. That's where the oldest reefs in the world are from. You want to be up there, Pip Pip? Oh. Are currently known, I mean, those rocks are all along, or those sediments that became those rocks are all along the Laurentian margin. So, but it's just, I think, more buried, less glaciated, just not exposed in the same way as they are up at Chazy or up at Isle La Motte with these in the Chazy group. So, zeroing in even further, we have a cross section. So, in this image, in slide 14 here, you see line B. They've placed a cross section here, and just to help us picture it even better, and they to orient you in the cross section, they put geographic markers here below this zone of the cross section called the Champlain Valley. We see, reading from left to right, Isle La Motte there, and we also see the surface of the earth. This is an important, that horizontal line kind of running through the middle of the cross section where it's at sea level over on the left. we have the surface of the Earth just above sea level, so so much erosion has taken place, of course, since for example, the early Permian with 280, with those huge mountains right on the equator, split apart, and but various things have happened, and I don't know, you can pause this and read the descriptions of the different groups of stone. I've put them in here, starting with CPT on the bottom, right on top of the Precambrian basement. The Precambrian basement is called YU, and CPT, and reading up through all those units, I've put everything there up through OIB. And starting with the Potsdam Sandstone, the Beekmantown group, the Chazy group, undivided. That means that's all three of the ones that are divided out in this in the overhead view. Day Point Formation, Crown Point, Valcour, and then up on top of the Chazy group, we find the Glen Falls limestone. We're getting more recent in time, right? We're moving from the Cambrian into the middle Ordovician, into the upper Ordovician, and the Stony Point Formation, and then the Iberville Formation. And some interesting things about this map are this cross section stand out here, right? So if we look right in the middle of the pink zone, in that layer OSP, the Stony Point Formation, we read that's a dark gray calcareous shale with beds of bluish gray limestone. Shale, keyword shale, right? And the shale is thinly bedded, fine-grained sedimentary rock, right? Deeper ocean, and it's weak, and during the Alleghenian orogeny, when Gondwana was and La Rosa were just sutured, this faulting took place, and that weak shale a fault appeared, and there was this shoving of everything towards the west, present day west or northwest, and that's the Champlain thrust fault, and you can see it there right at the middle of the cross section, and you can see those arrows with one prong. They're going through the middle of OSP, the Stony Point Formation. And that's an amazing feature that I also visited, the Champlain Thrust Fault, but I have some good pictures. I didn't make a video of it. And finally, so we see here OCGU is all three. It's a thin layer. Just a few carbonates, but it splits up into three different varieties, and we see the underlying one has thinly bedded to massively bedded sandstone. So thick, massively bedded is just thickly bedded sandstone there at the bottom, and some fossiliferous limestone, because it's that beautiful shallow marine coastal shelf carbonate platform kind of world, God, this shit blows the mind. It blows the mind. I don't know. You live in this world. You have your little. You grow up. You have your cute little things, and then you realize, oh my God, it's this kind of vast epic epic place. Just so much time and so much life and time and life and time. This is a really, and then coming in here to the real specific studies, right, of the Chazy group. And here we're not even looking at the underlying, if we go back here, we're not even looking at the day point formation. We're just looking at we are day point, crown point, Valcour. Yeah, there it is. Day point. And so we see the sandstones are, if we look at the legend here, dolomite is the tilted carbonate there. Limestone is the up brick, just the up and down brick. Dolomite is a limestone that's been chemically reworked with magnesium, and it's much more resistant than limestone. It doesn't dissolve as much, or maybe at all, in the rainwater. I forget about that. But it's mixed in with the limestone because it's a similar depositional environment. But sandstone there is where we should start with. So right on top of the Bridgeport dolomite, we have the underlying, thick to thinly bedded sandstones from the Tectonic mountains. But in this continental shelf environment, this foreland basin world here, there on the Laurentian margin around 460 million years ago, we see these reefs coming into being, and they start out at the bottom there with those, oriented linear mounds. I have to look into all this language. Instead of circular mounds, instead of erosional mounds, and instead of flat plates, those are all different shapes reefs can take. We start out with oriented linear mounds, okay? And in those mounds, we have those little sheet bryozoa. Interesting, so I don't know if the mounds I think the mounds are maybe stromatoporoids, which is maybe the earliest reef-forming organism. It's kind of like a sponge, but before a sponge, and it's not even in our list of fossils here on this slide, but it is one of the fossils there. I think it forms the early mounds, but I have to look into that. And then we also have sheet bryozoa. Maybe the sheet bryozoa actually are forming the mounds. I don't know. I got to look at it. And they have it set up in this interesting way, with the interbedded with limestone. So the reefs are not covering everything. They're just beginning. There's these nubs, right? But if we go up through the day point, geologists, they've made this generalized stratigraphic section, right? Pitcher, back in 1964, made this generalized stratigraphic section. And by traveling around on Isle La Motte and other places where the same crown point formation, day point formation, etc., are exposed, put together this generalized stratigraphic column. So it's just a kind of handy guide. It's not a real formation or anything. It's just a kind of what they have been able to see, all put together into one thing. So anyway, cyclostome bryozoa, moving up the day point formation. What the hell is that? Some interesting shit. I don't know anything really about these animals. They're just a little my knowledge is a little cartoonish. It's kind of, I have watched some videos. I have learned about cephalopods. I have read about cephalopods, but trilobites, I know a little bit from just trying to watch a bunch of videos about paleontology. But anyway, in this generalized stratigraphic section, we don't see trilobites, incidentally. I don't believe. Oh, wait. Are they sponges? Yeah, see, they're not in the reef, they're not among the reef organisms. I don't know exactly why, why that would be. Wouldn't we expect them to be there? But yeah, see, you can pause this and spend, again, this is another image that you can spend a million years looking at, and literally, and always seeing something new. And, we're just going to try and keep this in mind as we look at these fossils. I think it's actually worth just reading through some of the descriptions of these fossils, because my knowledge doesn't go beyond these descriptions, really. So this is all we're going to have as we look at these fossils. And it's okay, we can learn more later. This is just a fun excursion. First of all, let's start with the crinoid, the sea lily, the what's another word? Not brachiopod, echinoderm. That we were looking at some of the columnals earlier, and you see that there's those three columnals on the crinoid down there. And it's important to remember, we can zoom in here. Anyway, crinoids are related to starfish. They're five-pointed, just like starfish, and sea urchins. Five-parted, in the way that plants can be three-parted, six-parted, their flowers and so forth. They look like plants because the animal lives in a cup atop a stalk of columnals. Most often, only the fossilized columnals are found. And I just want to note here, it looks like the two columnals we were looking at might have, been from different portions of the stalk. So at one point I was like, oh, that one's been squashed. But maybe it was the columnal from higher up, like this one at the top with the longer, wavier star rather than the tighter star. And yeah, it opens out into this cup with these fun filtering arms, I guess, that sort of contain floating microorganisms, and then they get sucked through and just eaten. And that's a crinoid, and growing, I think, fairly thickly, maybe getting munched by big fishies at this point. Grazing munchers? No, fish? Oh shit! Don't quote me on that. In the Ordovician. Fuck, I was learning about this a while ago. I was learning about fish a little bit, but no, the Devonian is really the fish. The time of the fishes. The Devonian, I think they call that the quote-unquote age of the fishes, which is kind of weird. Age of this, age of that, whatever. Yeah, but maybe there's something to it. I don't know. Yeah, maybe we'll read these descriptions as we meet them in the field, and we'll just leave it there. Have I begun to do justice to the epic story of, that can be churning, moving geologically in our heads as we get down and dirty with these fossils? Have I? Boiled it down, I guess, to 15 slides, I guess. Some sense of this epic totality of time, that it just enfolds us all, whether we like it or not, and also provides a platform, as it were. This is deep shit. I don't know what to say. More could be said. But yeah, I think we're gonna go back to go back to the real world, leave the world of analysis and synthesis, and I'm trying to do a synthesis. I would love to just live for a season up on Isle La Motte, which we can add in some more recent things. I mean, the layers never stop layering, in a sense, if we really get concerned with time and preoccupied with it, as some of us are. And in the present day, Isle La Motte was the scene of a grisly and gruesome murder in the early 2000s. I think most people take these murders as isolated events, weirdos. They other them in that way, but actually they're very typical. And, our world of death is a human world of human death as well, even though paradoxically that all that death is turned into value and capital and some grim stuff. And it manifested there on Isle La Motte. I mean, I'm sorry to talk about it as a symptom, but I think it is a symptom. I mean, yes, I'm not minimizing the moral enormity of what was done by these ghoulish teenagers who murdered their neighbors, I believe, and knifed this older couple to death around the time another older couple was knifed to death in Dartmouth. So, Vermont, New Hampshire, these are places of death. And then they burned down the house to try to, they thought they had a bunch of money, this safe full of money, these sociopathic teenagers, I guess. And they took that safe, but I don't think it was full of money. And people were shocked, right? But you go to Isle La Motte, I don't know, it's a little creepy up there. It's a little creepy. It's a little sad. It's growing up in sort of real mass extinction type environment, cedars, but they're not cedars, they're junipers, actually. Those are mass extinction trees. They'll grow anywhere. They'll grow in disaster zones and quarries and so forth. So there's more to say, but underneath the feet of those sociopathic teenagers was this just moving, beautiful crown point formation, just thick with life. These mounds, these reef mounds, and just full of all this beautiful shit, beautiful life. Making a reef for the first time in world history. I mean, pretty much. It wouldn't be this reef in this place. It's the first reef ever, but this is the oldest known, and so it's probably not much older, right? There's probably not. It's representative of this moment, this incredible turning point in the history of life, in which, these small marine organisms, corals, bryozoans, stromatoporoids. The stromatoporoids are a special mound within the mound. Yeah, I'm starting to get, you just have to sit with this and really read it. Under the feet of those teenagers was this gorgeous glory of life and time, and it's faulting and just generous, a generous world of abundance. But yeah, We'll go back to it.